So now we are going to start sort of exploring a little bit of the statistical math behind a lot of the things we are going to do, right? And so we started out with the stock market example, and we are going to get to a point where we can build a robust or efficient portfolio using some of the math, okay, behind it. Very simple. It might look a little bit how do I say? It might look complex, but I think if you spend a little bit of time and read through it, and of course, if you have anything to discuss, I think I'm always available to help. But what I'm saying is that don't be frightened by looking at these big things. Okay, so let's talk about random variables, right? Unexpected value, variance, and standard. We're going to talk about all those things. Let's talk about random. So a random variable is basically a numerical description of the outcome of a statistical experiment, right? So it's a way to map outcomes of a random process to numbers. For example, okay. Uh, uh, Whenever a random process may be thought of as a process where the outcome is sort of not certain, right? It's sort of stochastic in nature. A big word, okay. So take for example tossing a die, right? We don't know in advance, right, what number will come up. Or similarly, like say flipping a coin, right? We don't know whether it's going to be heads or tails, right? So when we toss a die, this is an example of a random process, okay? And the number that shows up on top is the value of that random variable, right? And so say we are trying to buy into a pizza franchise, right? And being a numbers gal that you are, right? You get your hands on historical data on inflation adjusted profits for similar franchises across the country, right? And we know what inflation is, right? Inflation is the steady march in the rise of things, steady march in the cost of what or cost of things over time, right? So you always want to account for inflation whenever we are looking at historical data, right? So a dollar in 1950 is not the same as dollar today, because the amount of stuff the dollar could have bought in 1950 is different than the amount of stuff it buys today, right? So you want to account, and that's because of inflation. Um, that's Inflation, by the way, is naturally built into our system, into our economy, and it's by design. So you want to make sure that whenever you are investing, right, or whenever you're doing anything with where money is involved, you want to always outpace inflation. Otherwise, you're going to fall behind, right? So going back to this pizza franchise example, right? Uh, let's say 20% of them across the country. Let's say you have data on them, right? Clear say $70,000 in profits each year, right? 40% do $110,000, then 25% $180,000, and the remaining 50% say do $300,000 in profit, right? So the random process here is the pizza parlor making profits, okay? And the random variable X is linking that process, okay, to outcomes in dollars, right? So for example, 70, 110, 180, and $300,000 are the outcomes of that random process of that pizza parlor making profits, right? And of course there are probabilities associated with that, right? uh, and graphically we can look at it this way, right? You have this different probabilities associated with different amount of profits that pizza parlor makes, right? So what's the probability of you making, say, opening a pizza parlor if you wanted to go into that business of making $100,000 or less? You sort of add up these two probabilities and you get that number, which is zero point 0.6, right? So, uh, uh, the chance or the probability of you making more than $110,000 by opening a pizza parlor, oh sorry, less than, right? So okay, what is the chance of you making less than $100,000 or less, $110,000 or less? The chance is 60%, right? So 60% of the time you technically it's very likely that you're going to make $110,000 or less, right? So So variables that take on a value which between two specified values are continuous random variables, right? For example, height, weight. So these are continuous variables, and variables that take on in dollars. Okay, dollars is a continuous variable because you could make $70,000 and 25 cents, right? So that's a continuous variable because it can take on any value. And the ones that take on distinct values are discrete random variables, right? So, for example, a random variable representing the number of automobiles sold at a particular dealership on any given day is a discrete random variable, while the weight, as we just talked about, is a continuous variable, right? So that's just a way nomenclature difference in terms of how the variables are sort of coded, right? Uh, so let's define another random process, say of flipping a coin, right? A fair coin, right? Of course, you're not going to flip an unfair coin because you know that. And if you do know, if you do flip an unfair coin, you would not want to know the probabilities of each case in case you are about to bet on it, right? So let's say you're flipping a fair coin, and let's assume you win $1 if the coin turns of heads and nothing if turns of tails, right? So notice that we have taken this random process of flipping a coin, and mapped the outcome of the random process to the values of 0 and 1, right? Which is a dollar gained versus nothing gained, right? But nothing lost either, right? If tails, right? So 0 or 1, right? So we have quantified this process, and similarly we can quantify any random process like rolling a die, as we just talked about, playing the lotto, okay, lottery, or anything and everything we want to analyze, right? Now you must be thinking as to what am I talking about and how does it relate to the stock market stuff we just went through, and how does it apply to the rest of the stuff we're going to talk about in the course and in real life. Okay, so everything is basically uh, uh, anytime you deal with a data set, right, it's going to be something which has going to have uncertainty around it, right? So and that's what we're trying to sort of characterize and conceptualize mathematically, right? So going back to that coin toss example, right? So should you take that bet? Should you take that bet where you win $1 if it turns of heads versus not losing anything? Of course you would, right? Because we stand to gain $1 on one end and not lose anything on the other end. Okay, let's say you might not win $1 in the first attempt, right, or the second or the third attempt, because there is a chance that you flip that coin 10 times. There is no guarantee that you're going to get heads in any of those 10 times, right? It's statistically very, very unlikely to have that happen, but you could actually have this very, very less likely event of ending up with 10 tails in a row, right? That is a chance, right? But you know that if you were to do that coin flip experiment, say 100 times or 1,000 times, okay, you know that on average you're going to have 50-50, right? 50% of the time it's going to be heads and 50% tails, right? So the expectation of X, which is what would you expect to make with that experiment in terms of profits, right? In terms of law, in terms of making money, okay? There is a positive outcome because you win $1, right? So the expectation of X in that coin flip case, which also happens to be a discrete random variable because you only have two choices, 1 and 0, okay, is defined as so E of X, that's expectation of X. You basically look at the outcome, which is $1 multiplied by the probability of that outcome. So $1 times 0.5, right? So that means it's 50 cents, okay, at the first try, plus, so this thing is summation, right? So you basically, depending upon number of attempts you make, right? So let's say the first toss, which is I equals 1, the second toss I equals 2, the third toss I equals 3, and so on. You do it until n times, right? So the expectation of X is is 1 times zero point 0.5 plus if you get another head is 1 times zero point 0.5, another head 1 times zero point 0.5, then you get a tail is 0 times zero point 0.5 and so on. So you add all of them up, okay, and that's what you get, right? So the expected value of that coin toss experiment one time is 1 times zero point 0.5 plus 0 times zero point 0.5 is 0.5, right? If you were to do it say 10 times, okay, we might not win say $5 because if you were to repeat this 10 times, you're going to have this value multiplied by 10, right? Because if you were to do the math, right, the first time, let's say you get 1, okay, 1 times 0.5, second time let's say you get 0 times 0.5 and so on. So if you keep repeating it 10 times, depending upon what you get, you might not get exactly $5, okay, but if you were to repeat that say 10,000 times, right, you know that the odds of equal heads and equal tails are going to be very, very likely, and you're going to be very close to $5,000 of win, right? So expected value basically is the long-term average of the outcome of an experiment, right, over a large number of trials, right? So every time you flip a coin, that's a trial, right? So I'm not sure how clear that was, but let's go back to the pizza franchise example we were talking about, right? So the mean, okay, and that's where, so expected value is nothing but average and mean, right, or mean, right? And we talk about average all the time, right? So average of 5 numbers, or average weight of this 10 people is this much, the average height is this much, and so, right? So we talk about averages a lot. So we already intuitively know what it is, and we're just talking about it in an expected sense, because this is what we are going to do to make an inference later on say a population. What's this? So between population and sample, right? So you're going to take the sample data, you're going to estimate the average of that say sample or the mean of that sample, whatever you're measuring, right? So whenever you are dealing with a data set, you're never going to have the population data, because as we just discussed, population is impossible to sort of get data on, and it's very difficult to sort of it's very expensive to measure population data, and it's almost impossible to do that, right? It's probably impossible as well, right? So you'll always be dealing with sample data, and you're going to infer based on that sample as to what the population characteristic looks like, right? And that's all this inferential statistics is all about, right? So let's go back to the pizza parlor case. So what is the mean or expected profit you expect to make owning that franchise, okay? So you can say 20% of the time, 20% of the pizzerias which were out made $70,000. 40% of them made $110,000. 25% 180, and so on, right? So you add all of them up, and you come up with $148,000, right? So you might not make this exact amount, but based on past data, you should expect you're at least likely to make this, okay? Let's say the random variable this time is stock market returns, okay? And stock market returns, and let's say we have data on the last 3 years of returns, okay? Mapping that variable to actual data, right? So your random variable this time is, so the random process is basically the stock market actually generating that return, okay? Stock market doing whatever it is. And the random variable is linking that process to the outcome, okay? The outcome is it made 10% in 1 year, year one, it lost 8%, okay? So this is 0.1 is 10%, of course, minus 0.08 is losing 8%, and 0.15 again is gaining 15% in year 3, right? So you mapped a random process of stock market returns to an outcome which is this 3 data points, right? So the probability, so the likelihood or the probability of any of these returns occurring is 1/3, right? because you have only 3 data set, right? So the likelihood of this happening in this 3 data set is 1/3, right? So because you have 3 instances, so 1/3 of the time you have this, 1/3 of the time you have this, 1/3 of the time you have this, right? So the probability is 1/3, right? Because that's what you have number of years, and year 1 you got this, so 1/3, 1/3, 1/3, and you have this different outcomes. Okay, so the expected return of this 3-year stock market data is 5%. Okay, 5.66 some odd percent, right? So similarly, if we had 5 years worth of data, the probability assigned for each year of data is going to be 1/5. If we had 25, it would be 1/25, and so on, right? So we can sort of approximate this thing, okay, by doing expected return for a whole bunch of data, right? Say you have 100 years worth of data, n would be 100, and then you sum up all this return, and you take the you do this math, okay, and you come up with the average, okay. So this is basically average. This is how you calculate average, right? So you have five numbers, you add them up all, or add them all up, and you divide it by the number of those events, so the number of occurrences, and that's you get an average, right? So let's go back to that. So let's stop here. So we talked about expected return. Okay. So let's continue with variance and then standard deviation. Okay.